Alright, chemists. So today we're about to get quite deep, I suppose, into acid theory or theory of acids. So we're going to talk a bit about the history, and then we're going to talk about what the current idea is, or at least the idea that we work from a high school point of view. And we're also going to look at deciding what an acid and a base is according to the current theory, and something called conjugate bases and conjugate acids. All right, so the point of today is to be able to identify, just give give an outline of the history of the theory of acids. You also be able to identify what a Bronsted-Lowry base is. There should be a little dash in between there, and you'll be able to identify conjugate pairs. So what do we need to remember? We need to remember what an operational definition is. So this is a definition which is useful, okay? So we can base it on our observations, and it's something that is a useful way for us to proceed. The earliest concept of acids really were operational definitions, and they were based on observations such as the following. Basically, they decided sourness, so they've just gone, this is sour, therefore it's an acid. An ability to change the colors of indicators. So it wasn't anything remotely close to a correct definition of what an acid is, but it worked, and that's what an operational one is. So it's a definition that works for what you need it to do. Then there's conceptual definitions, and these are the way that we use to explain observations. Now, it's also closer to a theory, so it's actually much more complex. It doesn't just say, this is what happens. It says, this is what happens, and this is why it happens. So basically, as we've traveled on in chemistry, we've gone from operational definitions to conceptual definitions, but we still, for a working scientist, a working chemist, in many ways, the operational definition is as important, if not more important. So let's look at a bit of our history. We've got Antoine Lavoisier. He was the first one to really come along and say this is what an acid is. So he came up with the idea in 1766 that the acids were anything that contained oxygen. Now, he based this on the fact that non-metal oxides produced acidic solutions. This obviously was later disproved, so many basic contained, I should say, no oxygen. Many basic substances were found to contain oxygen. No, hang on, I'm an idiot. Scratch that, I was right. Either way, it's wrong, it doesn't matter. So we found out that basic substances had some oxygen, some acidic substances had no oxygen, like hydrochloric acid, so therefore it's not substances that contain oxygen. Then we have Humphrey Davy. In 1810, he came along and he decided that acids were substances that contained hydrogen, and you could replace these with metals either totally or partly. Now he's closer, okay, because we know that acids have hydrogens. So this was based on the observation that when acids reacted with a metal, the metal replaced the hydrogen, which means a hydrogen gas was evolved or given off. We can see this when we put hydrochloric acid with our magnesium. And then we have SVANTE ARRHENIUS, and he has, for a long time, he had the definition. It was the key one for nearly 50 years. And he basically came up with acids were substances that ionized in solution to produce a proton or hydrogen ion. Basically, they were strong if they ionized almost completely and weak if they only ionized a little bit. This is true, but it ignored the solvent, the water in the situation, which we'll come to have a look at when we look at conjugate base pairs. So yeah, he was almost there, but we just replaced him a little bit with the Bronsted-Lowry one. Which, let's look at this one. So this is our key one. So there should be no E there either. I really should proofread this stuff properly. So Thomas Martin Lowry and Johannes Nicholas Bronsted, they came up with these two ideas independently. Basically, an acid is a proton donor. So anything that gives an H plus ion. Base is a proton acceptor, so it's anything that takes that H plus ion on. Now, we'll give you a slightly more simple one in a minute. If a substance has a greater tendency to give away a proton than the solvent that it's in, the solvent will be an acid, okay? If substance has a greater tendency to take on the protons than what it's with, then that solvent will be a base. So if it takes on, so if you've got two things dissolved together, the one that is more likely to give away a proton, that one is a base. So the solvent is anything dissolved in it, by the way. So we've got, if something is more likely to accept it than the other solvent, it becomes it's then a base. So giving away acid, accepting a base. It just pretty much gets rid of most of the difficulties, and it's the most widely used one today. So if you look here, we'll get rid of that one. What we have here is we have our NH3, okay, and we have water. In this case, the water gives up the acid to make NH4 plus, and we've got a hydroxide ion left. So according to this, this one gives away a hydrogen. So here the water is the acid, and here the NH3 is a base. All right, and we can see that down here. HCl is an acid because it gives up a hydrogen. We'll come to these phrases in a second. Water is a base because in this case it accepts it to make a hydronium ion. Okay, so very simple. Now, let's look at the idea of conjugate bases. So a conjugate base is what is formed when an acid gives up its proton. So here's the acid, and that there is its conjugate base. It's formed when this acid gives away its proton, so it's just there. It's all about having the opposites evening each other out. So the conjugate acid of a strong acid, as a conjugate base of a strong acid is an extremely weak base, which means it's too weak to start pulling this back. Okay, it'll never pull that back, and the reason it won't do that is because it's a weak acid. It's just the way it's going. It goes to completion the other way. The conjugate base of a weak acid is also a weak base. So a conjugate acid. So here's our base. So what's formed when that pulls on the extra hydrogen ion is our conjugate base. And the opposite is also true. So the conjugate acid of a strong base is an extremely weak acid, and it doesn't react with the solvent. Now, when hydrochloric acid, which is a strong acid, reacts with water, a very weak base, a hydronium ion, and a chloride ion, which is the weak conjugate base, hydronium ion is a strong conjugate acid, are formed. All right. So we want to be able to look at these and identify them. And to basically, it's the conjugate acid which gives the particles the solution's acidic properties. You need to remember that. And you need to really look at the whole thing before you can decide which is which. For example, if we were to ignore this stuff down the bottom here, so we've got NH3 and water. This is the base, this is the acid, because once we look at the entire solution, we can see that this is taking on an extra hydrogen ion, and this is losing one. If we come over here, here's acetic acid. So this is our acid, so acid to base, okay? And here is our base, base to acid. And here's a more complex one where we've got two of them. So acid base, base, base to acid, and over here we've got the base to our acid and the acid to our base. Okay, because here it gives up the hydrogen and here it accepts the hydrogen, which means on the other side. So you really need to look at the whole solution to work it out. All right, and that's it. I hope that made sense.